Here in this video, we're going to talk about the identity matrix and inverse matrices. First, let's discuss what identity matrix is. The identity matrix, we're going to call this I. It's a square matrix that when we multiply it with another matrix, we're going to get that matrix back. So let's build on this idea. If A, this non-identity matrix, it's an n by n matrix, so that's a square matrix, and I is the identity one. It also has the same exact dimensions as A. If we multiply A times I and we try to do I times A, we will get the original matrix A back. So let's build on this idea of identity, and let's connect it to something that we know. We have what we call a multiplicative identity. We don't really refer to it in that words because we're so used to doing it. But what we're talking about is if we did 1 times 3, we know that that is 3 because 1 times anything is the number itself. It's an identity. It gives us back our original number. The same as if we did 3 times 1, it is still 3. This idea is being expanded into the matrix world. What are those identity matrices? We're only going to look at two types right now. We're going to look at a 2 by 2 matrix, and we're going to look at a 3 by 3 matrix. What an identity matrix is for the 2 by 2 is where the main diagonal, the top left entry, is going to be a 1, and the bottom right entry is going to be a 1. Every other entry is just the number 0. For a 3 by 3 matrix, the main diagonal, the top left, the middle entry, and then the bottom right entry will all be 1s. Everything else will be a 0. So if we can take a matrix and multiply it by these identities, we will get the original A matrix, or whatever that matrix happens to be labeled, back. So that's what an identity is. So if you see I represented by an identity, you need to keep in mind what are the dimensions, and the main diagonal is all 1s. All the other entries happen to be 0. What we can then say is two matrices, 2 n by n, these matrices have the same dimensions. We're going to call them A and B for now. They're called inverses of each other if and only if their product, so if you try to take A times B and you also try to take B times A, you get the identity matrix back. Again, let's make sense of this here. Let's look at our real number world. All real numbers have a multiplicative identity. Let's stick with 3. We need to say, 3 times what number would give us 1 back, our identity? We know that as 1/3. That would be the multiplicative identity here. And we also know that if we were to take 1/3 times it by something to get 1, that would be 3. Those two are called multiplicative identity. They're the multiplicative inverse, So 1/3 would be the inverse of 3, and 3 would be the inverse of 1/3. We expand on that idea with matrices. So let's look at a few examples. We're going to try to multiply two matrices together. If we get the identity matrix back, then we know that they are inverses of each other. If we get anything else other than the identity, then they are not inverses. So let's start with matrix A and matrix B. I've used colors here. So what I want to do first is let's do A times B, or red times blue. We know that what if we do matrix multiplication, we want to take the top row, multiply it by the left column, that we're going to get -5 plus 6, which simplifies to 1 in the top left. We then move on to the top row, right column, which gets us -2 plus 2, which in fact is 0. Then we go to the bottom row, right column. We get 15 minus 15, which is 0. And then finally, bottom row, right column, gets us 6 minus 5, which is 1. What we notice is that this matrix right here is our 2 by 2 identity matrix. So far we are good, but we have to check the other direction. Not only do we have to do red times blue, we need to do blue times red. So let's check that multiplication.
Teachers, for an interruption, if you could release the cheerleaders and the drum line at this time.
So as I was saying, let's take blue times red. Let's take the top row multiplied by the left column, and we get negative 5 plus 6, which is 1. Take the top row times the right column, gives us 10 minus 10, which is 0. Take the bottom row times the left column, gives us negative 3 plus 3, which is 0. And then finally, the bottom row times the right column, 6 minus 5, which is 1, and both times we end up getting the 2 by 2 identity matrix, so then we can finally say, yes, these two matrices happen to be inverses of each other. Another example. Let's take R and let's multiply it with S. If we get the identity matrix, let's go in and check S times R and see if, once again, we'll get the identity. So we start with R times S. Red times blue. Top row times the left column. We get 48 plus 48, and we get 96. So it kind of looks like we're on the way here that these are not going to be inverses, but we're going to go ahead and check all the rest of the terms. Top row, right column. We get negative 16 minus 15, which gives us negative 31. Bottom row, left column. Get negative 24 minus 32, which is negative 56. And then finally, if we did the bottom row in the right column, we get 8 plus 10, which is 18. And I don't have to go in and check S times R because R times S does not give us a 2 by 2 identity. So therefore, these are not inverses of each other. So what this says here is that not every matrix has an inverse. Whereas we have real numbers, they all have inverses of each other, but not every matrix is going to have an inverse. How will we know when a matrix doesn't have an inverse? Well, if you're given a matrix and its determinant happens to be the number 0, then we can verify that this does not have an inverse. And here's why we know this. To find an inverse of a matrix, you're going to take the original matrix that you are given. You need to double check. If it doesn't have a determinant of 0, then the inverse matrix, A inverse is how we would pronounce this notation here, A inverse, is equal to 1 over the determinant of A times the following matrix. What I want you to notice is that the original diagonal of the given matrix, AD, those terms, those entries, those elements get switched, while as the B and the C stay in the same position, but you do the opposite value of what is there. Okay, let's put this in action. So if we want to find an inverse of a matrix, if it exists, so here's a matrix A. Before we even follow through to try to find the inverse, we need to check its determinant. So what is the determinant of A? Well, first we do 4 times 3, which gives us 12, and then negative 1 times negative 6, which is 6. We always subtract between the two numbers, and its determinant is 6. So since that is not a 0, this does have an inverse of it. Let's find what that inverse matrix is. Following the definition of an inverse here, we go 1 over our determinant, and in our matrix, we switch the A and the D. So 4 goes to the 3 spot, and 3 goes to the 4 spot. And then for the negative 1 and the negative 6, we're just going to drop the negative signs because we do the opposite. Now what you should notice is that this 1/6 happens to be a scalar. And we can do scalar multiplication where we just distribute the 1/6 through with all of our fractions, with all of our numbers there. And what we will end up getting this is the following matrix. 1/2, 1/6, 1, and 2/3. That is the inverse matrix of matrix A. And if you wanted to, you could take this matrix and multiply it by this matrix. You're going to get the identity matrix back of 1, 0, 0, 1. Let's try another one. Here we have matrix B. We need to check its determinant. We take our diagonals and multiply. What you should see then is we get 8 times negative 1, which is negative 8, and we're going to subtract from it negative 4 times 2, which is another negative 8. We get a determinant of 0. If this number happens to be a 0, we stop. Remember, if we have a determinant that is 0, this does not have an inverse. So we'll just stop, say B does not have an inverse, and we're done. Okay, let's look at another one that does have an inverse of it. So matrix C, check the determinant, take 8 times 5, and then negative 10 times 8. And its determinant is 120. So we're going to use that number now. Using the definition of the inverse matrix, 1 over the determinant of our original matrix, we will take the main diagonal, we're going to trade places with the numbers, and then the negative 10 and the positive 8, we're going to flip-flop their values. Keep the numbers in the same spot, but trade their values. So negative 10 goes to positive 10, and 8 goes to negative 8. And then finally, we can take our scalar multiple on the outside and go ahead and distribute it through all 4 elements. And we get the following matrix here. We get the 1 over 24, 1/12, negative 1/15, and positive 1/15. And that right there would be your inverse matrix. And there's a short video over finding inverses of matrices and determining if the two matrices have